Bismillahirrahmanirrahim. Welcome back to my channel. This video is going to be on windowing function that we normally use when I take FFT of a signal. And so we're going to see what type of windows, what are the behavior of different windows that I have available. In order for me to show you this and practically show you, first of all, let's understand our flow graph first. So this flow graph is very important. For example, if you are using your RTL SDR dongle or any SDR device to capture your signal, you gotta know what type of windowing function I need in order for me to visualize my signal clearly without making any mistakes. So for that reason, we're gonna look at windowing function. So this flow graph is quite simple. I have a signal source that is generating a code signal. I have a sample rate that I have selected that is 128 kilosamples. Frequency, it's default frequency 64 kilohertz. So frequency in this slider, if you were to look at it, in this is being changed, made it variable using Qt GUI range slider, where I have a frequency, and this frequency range is from negative 128 kilohertz all the way up to 128 kilohertz, and my sample rate is 128 kilohertz. All right, and if you were to look at then the instrumentation, I need a throttle block, which is right here. And I have a Qt GUI time sync, and I have a GUI frequency sync. Notice one thing: when you just simply use that, you will have number of points to be 1024. I have changed this to 128. I'll explain this in a little bit. And when I look at this, now my FFT size, I also selected to be 128 bits. Now FFT, what does frequency sync does? It actually takes a Fourier transform of your signal. The reason I have selected 128 kilosamples, because if I divide samples, I can calculate number of bins. I can divide, so I have bin size of 128, and 128 kilo divided by 128 would give me 1000. At 1000 kilo, when I will start observing my signal at 1000 kilo, I will get multiple integers of that. So I'll have a frequency component which will be at 1 kilohertz. Of course, I'll have components from between 1 to 2 kilohertz, but those are not going to be your integer multiples. So in this way, when a component is not integer multiple, I won't be able to, that's where I'm going to use windowing function. I hope you're understanding this. The reason I have selected 128 kilohertz, and because in our Qt frequency sync, I can only select 32, 64, 128 in multiples of 2 to the power n, 2 to the power 1, 2, 3, 4. The reason I have selected 128 and having a sample size, because this is the number of bins. 128 are number of bins. So 128 kilo divided by 128 would give me 1000. So I'll have an integer multiples of my signal component. I'll make it clear in a little bit. That's why, that's the reason, that's the only thing. Otherwise, rest of the flow graph is quite simple. And let me just quickly run this flow graph and show you. So when I execute this flow graph, this is what you would observe. All right, so as you can clearly see, I have a frequency that goes from 128 kilohertz all the way up to 128 kilohertz, which means it goes all the way up to here and up to negative frequency. So default frequency is just half of that. If you were to look at it in my, so default frequency 64, so sample rate divided by 2 would give me this. So let's look at our flow graph. Let me change this flow graph. I want to do a couple of things. By clicking right click on this flow graph, I want to go to my data, and I want to change my marker to circle first. And right now, I want to choose my windowing to be a rectangular window. So this is what I would see. Let me change this frequency to around 1 kilohertz, and so I can show you this. All right, let's look at 1 kilohertz. At 1 kilohertz, you are exacting, so this is an imaginary signal. So you have a sine, you also have a cosine function. Both of the functions are, so this is your sine and this is your cos function. You are exactly at 1 kilohertz. You're seeing integer multiple of your signal. What I said earlier was this: you're seeing exactly one complete cycle of this. You're seeing exactly one complete cycle of your sine signal, which is in blue, and you're exactly seeing one complete cycle of your cos signal. Now, if I change this If I didn't have my bin size to be exactly 1 kilohertz, I would not see this. Let me change this to 1500. How many? You would see 1/2 of it. All right. So now you're seeing 1.5 of this complete cycle. All right. And if I were to select 2000, I would see 2 cycles. 1, and then you're seeing 2. 2 cycles of your sine and 2 cycles of cosine signal. That's why I have selected my sample rate to be 128, and I've selected my bin size to be 128, so I'll be able to see integer multiple of these components, which is at 1 kilohertz, 2 kilohertz, 3 kilohertz, and of course in between this. Now, let me just change this frequency back to 1000. If I were to look at this, look at my signal. Look at my signal. It's spot on at 1 kilohertz. Exactly at 1 kilohertz, and there is no leakage. Now let me change the signal a little bit. I have changed this incremental values. Check this point. Now here, observe here. Now when I start changing my frequency is no longer integer multiples, because when I'm taking a Fourier transform, I have to take frequencies in integer multiples. Now when I change this frequency, you would see this when I change this frequency, my profile is changing. All right, so two terminologies that you need to remember. This is going to be my main lobe, and these are going to be my side lobes. These side lobes, if you were to look at it at 1 kilohertz, you can do it for any multiple. They are just way down here. Let me just show you. The noise floor is somewhere around at -150 dB. Now when I change this to 120, all of a sudden my noise floor jumped to -50 dB. And you would start observing these points. It will start taking this signal, this point, which is the peak of your signal, will start taking over the next bin, as it's not going to be multiple integers. Just quickly observe this. Observe it right over here at this point when I'm changing my frequency. Now when you look at this, you see this? Now my noise floor has jumped tremendously. These side lobes are getting bigger and bigger, and my signal, the main signal, which is the main spike, is actually changing. I'm using a rectangular window, which is a general window right now. So when I change this, let's observe this right here at this point. At this point, you need to observe it at this particular point. Now when I change this, you see this? Now the bin start getting closer and closer. You start acquiring the next frequency bin. Now at exactly, let me just zoom in. Now at exactly 1500, now you have half here, half here. You guys are seeing this? You're not, if you were to just look at this peak, you are not getting the same signal, isn't it? Your signal is 1500 because now you have half of the power which is going into this bin and half of it is going to the other bin. If you can clearly observe this. Now, if you were to just bring this back here. All right, now when I start changing, look at the points. Now this point, it will start merging into a single point, which will make like this shape. Now quickly look at this when I change this. So this thing, when you start seeing leakage, which is coming from other bin to your main point, that is called a spectral leakage. All right. So let's just quickly look at it. And this is also known as scalloping. This concept is also known as scalloping, and this is a loss. Now when you look at it, as soon as I'm getting closer and closer to my integer multiple, look at my signal. Here we go. It's perfectly, and my noise floor is way down here. Let's just quickly look at my noise floor. Let me just hold on a second. Let me just press the center button and bring the control panel. When I look at my control panel, now let's look at this. My noise floor is somewhere around -200. Now, when it's not an integer multiple, look at my noise floor. It's there. Now these extra bins, that is actually causing now your lobes, these side lobes or these side points, they are getting even closer. Now the noise, this is somewhere around -26 as compared to at integer multiple. So now what windowing function does, it actually smooths this out. It smooths it out, and whenever you are not an integer multiple, it actually it actually maintains the profile of your signal. It actually maintains the profile of your signal. Let me just quickly show you what I mean by that. Let me right click and let me change my window. Let me change my window to something called Blackman-Harris, which is the most common window. Let me, you know what, let me just close this and let me run this flow graph again, and I'll show you this again. Let me just go to 1000, and so you can clearly see the difference. Right now, let me change this window to rectangular window. So we're at 1000, and let me just put a marker. So let me go to my data and then go to marker and then put a circle there. All right. So when you're not at integer multiple, just simply look at it. You see this? Your side lobes are all the way, and then you start acquiring the next bin. Now, at exactly 1500 kilohertz, you're actually taking care of the next. You're actually in the next bin as well. So you have 2 points. This is basically like a flat window. Flat. You have half power going here, half power is going to the next bin, and this is where the problem comes in. So this is where I need windowing function. All right. So rectangular window is not a very good window. So let me just go ahead and change this window to Blackman-Harris, which is one of the most common window. Now let's look at it at 1000. The signal is not much of a change. Look at this. My side lobes are way down here at negative 19 dB. When it comes to, okay, so that's good at 1000, but let me change this to integer multiple, and let's see if the profile of my signal is changing much. Not much. I'm seeing an increase in my side lobe. That's not it. That's you can still see that, but you're not seeing much of an increase in my side lobes. So when I change this, there's nothing much going on when it comes to, yes, there's going to be a spectral leakage, but it's not going to be as much. So at 1500 megahertz, you're still seeing a profile that quite similar, but your noise floor is way down here. Now when I look at 2000, is still, so at 1000, if you are at integer level, integer multiple, if you're not an integer multiple, it's still maintaining this profile of your signal that looks like this. That's why we use windowing function. Another type of window that I can use, let me just quickly run this and let me show you this. All right, let me just go back again to 1000. And let me just bring this. Let me just change this marker to circle. And let me just change this windowing function to rectangular function. So this is how the rectangular function looks like at 1500 megahertz. Let me just quickly change this. Alright, this is how it looks like. As you can see, your side lobes are quite high. It's not like properly smooths out. So now when I change this to your Blackman-Harris, look at this, how nice that function looks. So how are you going to choose your window? Choosing window is it's not an easy task actually. You got to remember a few things. First of all, if your signal, let's say you capture a signal, and if your signal contains a very strong interfering signal near your frequency of interest, right? If the signal contains a very strong interfering signal near your frequency interest, you need to choose a window with a low maximum side lobe levels. With a low maximum side lobe levels. So basically, so this is how you're going to select your window. Second, if the frequency of interest contains two or more signals very near to each other, then you need to select a window that has a very narrow main lobe. Right? When you have two or more signal near your signal of interest, you need to select a window that is very narrow lobe. So example being something like, let me look at, let's look at Kaiser. So this is the type of signal that you need when you have multiple signal that is interfering your frequency of interest. This is the type of window you need. If you need an amplitude accuracy, sometimes you are just only interested in your amplitude. You need to select a window that has a wider main lobe. What I mean by wider main lobe, let's look at Blackman-Harris. Wider main lobe. This is how you're going to select your window. If the signal is like quite broadband, if your signal is quite flat, which means it's a uniform signal that contains a lot of frequencies, then no window, which means a rectangular window. Basically what windowing is, think of it like this. Think of it windowing like this. You have a signal, you're multiplying it by another signal. So most of the time, when you think of rectangular window, it's easy to understand. It is quite easy to understand with a rectangular window, because a rectangular window, if you were to look at it, it's just a low pass filter basically. So basically you're multiplying its transfer function with the signal, and you're getting your signal out. So if you have a very broad frequency range, you're looking at a broadband signal, then no window or what do you call it, a rectangular window is good enough. Now let's look at two other windows as well. Now I also have a presentation to show you. Now if you were to look at this, so this is your Blackman-Harris. If you were to look at this, let's move this aside. So this is a response of your Blackman-Harris window that we are just looking at. So we have a window that looks like this, and let's look at it. Isn't that what our response looks like? This is how the response of a Blackman-Harris window, because I have chosen Blackman-Harris window. The other type of windows, which is very good, is actually your Hamming window or Hanning window. Now, if you were to look at this, you will have a similar peak type, but as you look at this Hanning window, which is in red, it actually tapers off. It actually goes towards all the way up to 0. While Hamming window, it remains like this. So we're going to show you, I'm going to show you the response of this. So this blue is Hamming window and this is Hanning window. So let's just quickly look at the response of this. Alright, let me just quickly change this to Hamming window. Here's how the response looks like if you were to look at this. So this is a response of a Hamming window. Yep, I have selected Hamming window, and this is how a response of a Hamming window looks like. It does not quite reach us to 0, but it does eliminate the discontinuity in your signal. So it's not reaching 0. On the other hand, Hanning actually reaches 0. So let's look at this in red. Let's look at the response. So this was Hamming. It's not reaching 0, but let's just quickly look at this. And let's go to Hanning window, and this actually reaches 0. If you were to look at this almost reaches 0, and this is quite similar to the response that we normally see for a Hanning window. Rule of thumb: 95% of the things that you are doing, 95% when it comes to signal analysis, the best window to use as per the literature dictates is Hanning window, which is this window. 95% of it. Why? Because you will get good enough main lobe. Let's look at it. It's not very fat. The main lobe is not very fat. All right, it's not very fat as compared to Blackman-Harris, but it has a good roll-off rate. It has enough width as compared to rectangular window, and it actually tapers off to 0. So it actually eliminates discontinuity in your signal. So most of the time, the best window to use, the literature suggests, it's actually 95% of the cases you can use Hanning window, and you will get a better signal. Let's look at it at 1500 megahertz. All right. So this is the basic idea regarding window. Now on my presentation, if you were to look at this, let me just minimize this quickly. And let me just minimize this quickly. Let me just bring this. So this is quite nice. It's a good summary of what type of an application requires what type of window. So when you're just looking at your ADC characterization, so when you want to characterize, you want to see the functionality of your ADC, Blackman-Harris, sine wave or combination of waves, you need to use Hanning window. So here's the thing, when you are only interested in amplitude, you can use a flat top window. So let's just quickly look at flat top window. How does it look like? So just simply go here and let's look at my windowing. This is my flat top. So it's quite thick because you are actually preserving your amplitude. That's what you're trying to preserve. And so flat top is good enough. And then you have Hanning window for narrowband signal. Then you have for broadband, you have uniform or a rectangular window. Remember when we said we have a broadband signal, when you have a lot of frequency content, you want to look at uniform window / rectangular window. You have closed space sinusoidal wave, you want to use Hamming window. And then you have some other windowing which are there. You have a response of an exponential, two-tone with frequency, close to close, but amplitude were different. So this basic idea regarding this, it depends on what type of an application you have. So as a rule of thumb, as the literature suggests, 95% of the time you're good with Hanning window, but you can also use Blackman-Harris. I use Blackman-Harris. It does a job. I mean, when you're looking at your signal, so to get a clear picture of your signal, windowing is a very, very important function. So I hope you like this small tutorial on windowing. If you have any questions, leave it in the comment section, and don't forget to like and subscribe to my channel.